Hello, Bearcats. In this session, we're going to discuss the trigonometry from the right triangle perspective. As I said in class earlier, you can use the right triangle perspective for all angles or all right angles, but I believe that if it is a special angle, in my personal opinion, that you should just use your unit circle knowledge. And for all other right angles, you should use the right triangle trig. However, there are going to be teachers and professors that you will have that will focus mainly on right triangle trig, so you do need to be very familiar with it. Let's first review what we already know. We know that sine, we've learned that sine is y, and I'm going to make it y over 1, which we also know is from geometry, which is opposite over hypotenuse, which will help us with our right triangle. I'm also going to write the y over 1. We know that in the unit circle, 1 represents the radius, so sometimes we're going to see it as y over r for radius, and I think that's very important. For cosine, then, we know that it is x over 1. From geometry, we know that it's adjacent over hypotenuse, and we could also say that that is x over radius. And for tangent, we know it's y over x. From geometry, we know that was opposite over adjacent. Now, I also want to discuss with you the reciprocal identities, and that's really important, and we have focused on those some, and I want to focus on those even more. There are really 6 trig identities: sine, cosine, tan, and their reciprocals. So the reciprocal for sine is cosecant, and that one you just have to know, and that is going to be equal to 1 over y. The reciprocal, we're just taking the reciprocals. Or it is equal to hypotenuse over opposite. Or we could say the radius over y. So it's just the reciprocals. For cosine, the reciprocal is secant, and you need to know which ones are friends. So sine and cosecant are friends, and cosine and secant are friends, and then we'll learn about tan and cotan in a minute. Alright, so secant would be 1 over x, or hypotenuse over adjacent, or you could say radius over x. All right, and finally, the friends with tan, the reciprocal of tan would be cotan, and cotan would be x over y, or adjacent over hypotenuse. Okay, so those are things you know. We've either learned this year, or from trigonometry, you knew your SOHCAHTOA, if you want to say it that way. The next thing we're going to talk about are our special right triangles. Our special right triangles are also something that you learned from geometry. So this is not new, but I'm just refreshing your memory on the use of them. We've talked a little bit about them in the last section just to tie in how we got those values on the unit circle. And again, I'm going to tell you that I believe strongly that you should just know the values for the special angles. But let's take a look at it from that perspective, because like I said, you will be using this. So for a 30-degree angle, your triangle would look like this. For a 45-degree angle, of course, it's halfway, and it would look like this. And for a 60-degree angle, it would look like this. I've just blown up the triangles below because it's a little easier to work with. From geometry, you know this is a 30, 60, 45, 45, and 60, 30. So we could go ahead and add the other dimension in there. Other degree. All right, and now we also know in our unit circle that we're going to use our radius as 1. Which you used to think of as the hypotenuse, and we're going to think of as the radius. So it's 1 in all of these. Now, let's talk about our 30-60-degree triangle. We also know that we're now talking that our x value is our cosine value, and our y value is our sine value. So just think of that way. So this is our cosine, and this would be our sine, and this is our cosine, and this would be our sine. The other thing we knew from geometry was that in a 30-60-degree triangle, the side across from 30 was x. The side across from, that would be 60, I wrote 30, across from 60 was x square roots of 3, and the hypotenuse, or in this case the radius, was equal to 2x. So knowing that knowledge, we're going to go ahead and figure out where those values that we discussed the last couple days came from. So if 1 equals 2x, then you would know that x would have to equal 1/2, right? That's just from this given information right here. So in our triangle, x then would equal 1/2, or sine would equal 1/2. And this side would be 1/2 square roots of 3, which would equal the square root of 3 over 2, which would be cosine, which we've already discussed. So we could go through and think through that, but I think just knowing those are important. Let's go ahead and talk about the 45, 45. In the 45-degree triangle, the legs were x, and the hypotenuse, or in this case the radius, was equal to x square roots of 2. So let's talk a little bit about that. How would we solve that? If we know that x square roots of 2 equal 1, then we would divide away the square root of 2 and we would say x equals 1 over the square root of 2. We could rationalize our denominator by multiplying both numerator and denominator by the square root of 2 and get the square root of 2 over 2, which is what we wanted. So we know that x is equal to the square root of 2 over 2. And the radius was equal to 1 in this case. So in this particular situation, then, we would have x being the square root of 2 over 2. And since they are both x, the square root of 2 over 2. Our sine is the square root of 2 over 2, and cosine is the square root of 2 over 2. And that's how we came to those values. Remember, those are the ordered pairs at the point on the circle. So we have the square root of 3 over 2 and 1/2. We have the square root of 2 over the square root of 2. And now we're going to do the 60. Oh, and I wrote that wrong too. 30. All right, so for 60, 30, things just flip-flop. We've already figured that out. We know across from 30 was x. We know across from 60 was x square roots of 3. And we know that the hypotenuse was equal to, or the radius equal to 2x. And we figured that that was 1/2. So we knew that this was 1/2. So in this case, cosine is 1/2, our x. And we know that this was 1/2 square roots of 3, which was the square root of 3 over 2. So sine was the square root of 3 over 2. And you know they just flip-flop, so you really wouldn't need to go through that. So that's, again, how we derive those values. But for your special angles, I believe it's really important just to know them. Just to know them. For all other right angles that we will be dealing with, you will want to go through a process and figure them out, or use Pythagorean theorem to figure them out, which is what we'll use quite often as well. All right, let's take a look at another way to look at these angles, just in a chart. Many people really like this little chart. I also use it sometimes, especially as we move further along and we're not looking at the whole circle always, we're just looking at particular values. I put them in this order on purpose because on my unit circle, I'm going to pretend like my unit circle's over here, then 30 is below, and then there's the 45, and then there's the 60, and so that kind of reminds me of their location on the circle, so that's why I put them in that order. Remember that your 60 degrees and your pi over 6 radians, or pi over 4, or pi over 3 radians are your theta or your rotation. Okay, it's how far it's rotated. It's the theta value. And remember that all of these are your values. So the value, when you're asked to evaluate, then evaluate at 60 degrees sine. 6 degrees at sine is the square root of 3 over 2. 60 degrees at the tan at 60 degrees is the square root of 3, and so on and so forth. Sorry. I would maybe write this down somewhere and see if you like this better than maybe just looking at the circle. If not now, later on, that will probably become an important thing for you. All right, last we're going to start looking at our fundamental trig identities, just all of our trig identities. We're going to get a few today, and then we'll keep adding to those identities throughout the course of trig. These first identities that we're going to talk about are called fundamental trig identities, and really you already know these. You didn't even realize that you were learning identities while we were talking about them, but you already sort of knew them before you even started the course, and I just wanted to review them for you. So our identities, remember that sine and cosecant are friends. So the reciprocal, we're talking about reciprocal identities first. The reciprocal identities, sine would also be equal to 1 over cosecant theta. And cosine theta would be equal to the reciprocal of 1 over secant theta. And tangent would be equal to the reciprocal identity of 1 over cotangent theta. And you're going to use the reciprocal identities. Probably one of the most used identities are reciprocal identities. I'm not going to write them all out, but the reverse is also true. So, or maybe I will write them out. So cosecant theta would be equal to 1 over sine theta. And secant theta would be equal to 1 over cosecant theta, and cotan theta would be equal to 1 over tan theta. Cotan and tan are special since they are really, you knew from our unit circle discussion that they're really y over x, which was sine over cosine. So you already really know this. So you know that tan is sine theta over cosine theta. And you'll use this quite a bit when we're solving things. And therefore, cotan being the reciprocal would be cosine theta over sine. Wow. Sorry about that. Write it correctly. Would be cosine theta over sine theta. Okay, you definitely want to stop and pause and make sure you have this written down and think about it as you're writing it down and make sure that you know that you already know this, but that you want to make sure that you've made that connection to their relationships. All right, I'll be right here waiting for you. These cofunction identities we use a little bit. We don't use them a lot. I'm going to go ahead and write them down. We can discuss them a little bit further as we start to use them. There's also a great explanation in your textbook you might want to look at when you get to class tomorrow. Just to open up your book to 4.3 and take a look at the explanation for cofunctions. Again, not used as often as some of the other identities, but they are used some. And again, it goes back to the relationship. So these follow the relationship, so that's why they're not too difficult to memorize. So sine 90 minus theta is equal to that reciprocal cosine theta. Therefore, cosine 90 minus theta would equal to sine theta. And you do need to know that. Tan 90 minus theta, cotan, that's its reciprocal, and cotan 90 minus theta would equal to tan theta. And finally, secant. Actually, these are not reciprocals. They're kind of the counterparts, cosine and sine. Tan and cotan always go together. And then the two reciprocals of sine and cosine, would be cosecant theta, and then cosecant 90 minus theta would equal to secant theta. So you might want to make sure that you realize that co-functions are like co-workers. Think of their ordered pairs as co. And so the sine and the cosine would go together. Your tan and cotan always seem to go together. And then since you haven't used your secant and cosecant, they would go together. That may be a good way to start to memorize those. We'll talk about those a little bit more as we begin to use them. Like I said, we don't use those as often, but we do need to be aware of them. We have one more set of very important identities that we're going to talk about that we will use often. So go ahead and write this down and ready for the last thing. All right, the last thing we're going to talk about right now is Pythagorean identities. Pythagorean identities, very, very important. I got a funny little way to remember these, but very, very, very important. And they're not the things that would normally go together except for sine and cosine, and that's the first one. There are all sorts of versions of these. You can manipulate these, and we're going to talk about that. But the basic three that you really need to commit to memory are that sine squared theta plus cosine squared theta equals 1. And you really know that that's like y squared plus x squared equals 1. Or x squared plus y squared equals 1, which is the Pythagorean, equals c squared. A squared plus b squared equals c squared. Very, very similar. And we can take a look at that if we wanted to actually put that in our in a right triangle, and we could with a radius of 1, and we could actually figure that out. But just trust me that you need to know that. The next one has to do with tan, and it's 1 plus tan squared theta equals secant squared theta. So the way I remember this one is tangerine sections. If you know what a tangerine is, the little oranges, and you break them into sections. And so it's 1 plus tangerines equals sections. That's where I get my tan and my secant. And that's how I remember they go together. So when I'm talking about Pythagorean identities, I'll say, hey, what about tangerine sections? So 1 plus tan squared theta equals secant squared theta. 1 plus tangerine sections. And then the last one is 1 plus cotan squared theta equals cosecant squared theta, and we say cotton candy for this one. For cot, that gets you this cotan, and then candy, that doesn't really spell candy, but it does start with a C, and that's the other one. So 1 plus cotan equals squared theta equals cosecant squared theta. you can think 1 plus cotton candy to help you memorize those. These are really, really, really important. Often we're going to be rearranging these to use them. So what if we wanted to solve for tan, for example, in this one? Then what we would do, we would move the 1 to the other side, and we would say tan squared theta equals secant squared theta minus 1. And we would need to be able to use that. So know that you are going to manipulate these into other forms. You could say 1 minus secant equaled negative tan. So you could move the secant and the tan, and you could say 1 minus secant squared theta equals negative tan squared theta. There's all sorts of ways to manipulate these, but that part you should be able to do pretty freely. You just need to commit these 3 to memory. So again, sine squared theta plus cosine squared theta equals 1. 1 plus tangerine sections, 1 plus tan squared theta equals secant squared theta. And 1 plus cotton candy, 1 plus cotan squared theta equals cosecant squared theta. All right, go Bearcats.